ICDEC 2022. I welcome you all again this early morning, 8 o'clock morning in India to Northeastern Hill University, Shillong. We are jointly organizing this conference that in the Department of Electronics and Communications Engineering, Northeastern Hill University, Shillong campus, and Department of Computer Applications, Northeastern Hill University, Tura campus, in collaborations with Comsys Educational Trust, Kolkata. I request our today's session chair, Professor Sarmistha Neogy, to okay, already if we are online, so have justice there, and Professor Saha to take the dash, and Professor Nivaran Das also to be here, though we are all in online mode. At the beginning, I'd like to give a brief introductions of our session chair. That Professor Sarmistha Neogy is a professor in the Department of Computer Science and Engineering, Jadavpur University, Kolkata. She received her PhD degree in engineering and master's as well as bachelor in computer science and engineering degree from Jadavpur University, Kolkata. I'm not mistaken. And she has many publications in Journal of Reputes as well as conference proceedings. Dr. Neogy is a member of Government of India Minority Community for Joint Technical Committee, and she is also senior member of IEEE and IEEE Computer Society. Dr. Neogy research interests are in the areas of fault tolerance in distributed system, reliability and security in wireless and mobile communications. She has worked in various fields of wireless and mobile communications, as well as security and privacy, wireless sensor network, healthcare-related data analysis, etc. And our completion of this, I hand over the mic to Dr. Neogy, ma'am. Please, you take control over the ma'am.
Thank you so much. And at the onset, I would like to thank the organizers of ICDEC 2022 to provide me with this opportunity. And I'm really today very privileged to introduce Professor Punam Kumar Saha as the keynote speaker in this conference. Dr. Punam Kumar Saha is a tenured professor of electrical and computer engineering and radiology at the University of Iowa since 2013. His research interests include deep learning, artificial intelligence, image processing, and quantitative biomedical imaging. He has published over 120 papers in international journals and over 300 papers or abstracts in international conferences. He holds numerous patents related to medical imaging applications, also served as an associate editor of the pattern recognition and computerized medical imaging and graphics journals, and in many international conferences at various levels. Currently, he is an associate editor of the IEEE Transactions on Biomedical Engineering and the Pattern Recognition Latest journals. He received the Distinguished Investigators Award from the University US Academy for Radiology and Biomedical Imaging Research in 2021, COE Faculty Excellence Award for Research at the University of Iowa in 2020, and Young Scientist Award from the Indian Science Congress Association in 1996. He has received several grants awards from the National Institute of Health USA. He is a fellow of the IEEE, American Institute for Medical and Biological Engineering, Asia Pacific Artificial Intelligence Association, and International Association for Pattern Recognition. He has served in several IEEE and AIMBE fellow committees. Today, Professor Saha is going to deliver his lecture on bone microarchitectural imaging in osteoporosis, recent developments and translational studies. So we all welcome Professor Saha to this session. So the mic is now handed over to Professor Punam Kumar Saha.
Can you see my screen? Yeah. Yeah. So thanks to
Yes, sir.
ICDEC organizer for inviting me to present this keynote talk, and thanks to Sarmistha for introducing me. And I just want to add one more thing, that both me and Sarmistha were actually classmates at Jadavpur University Computer Science and Engineering Department during our bachelor's and master's studies for almost 6 years. Is that right? Yeah. So thanks.
Thank you, Punam.
Thanks. So let me actually start. Okay, can you see my full screen?
Yes.
Okay. So today I'll talk about bone microarchitectural imaging in osteoporosis, some recent developments and translational studies that we are conducting at my laboratory. So I organized my talk like this. I'll first introduce what is osteoporosis and fracture risk, what are the current status of osteoporotic imaging, then the role of bone density versus microarchitecture in diagnosing or assessing osteoporosis and fracture risk, and then bone measures using multi-row detector CT imaging. This is actually a new research direction that I initiated in my lab. And then I'll actually give some key results from a few human studies, and finally I'll draw the conclusion and acknowledgement. So let's start with osteoporosis. So what is osteoporosis? Osteoporosis is actually age-related degenerative disease where, especially for women after menopause or men at older age after late 50s, we start actually losing our bone, and then bone. So this is actually a specimen from a healthy person's vertebrae, like who died without any bone-related disease, and this is actually a specimen from a cadaver who had actually severe osteoporosis. So you can see that here the bone metric is much more compact, it is less porous, and here it is actually more porous. So osteoporosis means actually porous bone. So due to this bone porosity, bone becomes fragile and actually are more susceptible to fracture. And you may have heard that people actually falling from a very low height, say for example from the standing height, they actually break their bone like a piece of glass, right? So those are called actually osteoporotic fractures. And nearly 40% of women and 13% of men in their lifetime suffer at least one osteoporotic fragility fracture in their lifetime. And major osteoporotic fracture occurs at hip and spine and forearm. The fractures at forearm occurs because when we fall, we actually use our forearm to protect ourselves, and that's how we actually break our forearm. Then you may have actually seen that like people after older people, they actually spine gets bent, and that is because of actually fractures, vertebral fractures or fractures at spine. But most devastating among all osteoporotic fractures are actually fracture at hip, and often the patients who suffer hip fracture, they have to go actually some surgical procedure. And studies have shown that osteoporotic hip fractures are most devastating, and it may actually reduce life expectancy by 10 to 20%. So that's a significant loss. And more than 3/4 of all hip fractures occur in women. Well, there are actually a few therapeutic options for osteoporotic, but in general, they are actually expensive, and more importantly, they are associated with serious side effects, especially for like studies have shown that osteoporotic treatment increases actually the risk of breast cancer, and also actually it increases the risk of osteonecrosis. Osteonecrosis is like a dead bone, and it's very painful disease. And therefore, it's important to accurately assess osteoporosis and fracture risk before we can actually initiate treatments. And also, actually, it is important that we should be able to actually monitor treatment response. Right? And here, the osteoporotic imaging plays an important role. It plays an important role in early detection of the disease and accurate assessment of fracture risk. So, in the clinical setup, the current clinical standard for osteoporotic imaging is dual energy X-ray absorptiometry, sometimes it's called DEXA, DXA. So basically, what it does is actually it captures two X-ray image at two different energies, and applies some simple math to actually remove the effects of soft tissue and fat, and therefore you actually get actually the areal the measure of areal bone mineral density. It is abbreviated as BMD, right? And these measures as actually is expressed in terms of T-score. So what is T-score? So T-score is like a population has a mean. For example, the woman at say age of 60, there is an expected mean of BMD among all women within that age range. And then the T-score is basically, it is how many standard deviations. So the population also has a mean and a standard deviation. So T-score is basically, it is how many standard deviation above or below that population mean, right? So if someone's T-score is 1, that means that person has actually good bone, and the BMD is 1 standard deviation above the population mean. But if the standard deviation is negative, that means the bone is worse compared to the population. So if someone has actually a T-score of say -2, that means it's 2 standard deviation below the population mean. And clinically, it is defined that a patient is clinically defined as osteoporotic if his or her T-score is less than -2.5. That means if that person is 2.5 standard deviation below the population mean, then that person is clinically diagnosed as osteoporotic. So this is generally the current clinical practice in terms of osteoporotic imaging. But DEXA being actually a 2D measure, it has actually several inherent and fundamental limitations. First, it is actually sensitive to bone size because it is a 2D projection. So if someone has actually larger bone, it will have greater 2D bone density. But that doesn't mean that the bone is good bone, because the actual volumetric density may still be low. Right? And then another major limitation is that it lacks accuracy in the setting of degenerative changes. For example, if someone has actually vertebral fracture, especially that happens mostly at vertebrae. So if someone has actually vertebral fracture, then it's actually there's a compression at the vertebrae, and the bone is compressed to actually a smaller volume, and therefore you get actually high density. But that bone is not a good bone, right? So in degenerative situation, it has actually significantly reduced accuracy. And because of this limitation, it has been observed in several human studies that majority of individuals who suffer from fragility fractures are often misclassified as not having osteoporosis. That is, their T-score is actually greater than -2.5. Most of the studies have shown that a large number of patients who suffer osteoporotic fracture, they are in the osteopenia group. That means their actually BMD is between, their T-score is between -1 and -2.5. Okay. So because of this limitation of DEXA imaging, people have started actually thinking beyond DEXA and going beyond DEXA, the first thing is actually to go to volumetric bone imaging and bone microstructural imaging. So let us actually try to understand like what is the major geometry of bone. So if we actually look at actually bone, especially at the end of long bone, well, bone has actually two major parts. One is actually the cortical bone. This is the cortical bone, that is the hard, solid bone that we see from outside. And then there is a trabecular bone. Generally, trabecular bone, there's actually more prevalence of trabecular bone at the end of long bone or at the central sites, especially at vertebrae. Right now, actually, cortical bone is denser, it is stronger, and it is stiffer, and it is actually like it is made to carry our body weight and daily strenuous activities. Right? But cortical bone, actually being solid bone, it can sustain greater stress, right? And therefore it actually plays an important role in carrying our body weight and strenuous activities. But it can actually sustain less stress before failing because of the solid nature of cortical bone. And therefore, actually, when you actually fall, that there is a sudden jerk, and that sudden jerk creates actually a short duration high strain, and cortical bone actually fails and suffers a fracture. And here the trabecular bone plays the role, because trabecular bone is more spongy, it can compress, and therefore it can actually sustain larger strain before failing. Right? And the studies have shown that actually osteoporosis can lead to thinning of both type of bone, which makes bone more susceptible to fracture. But there are also actually several studies that have shown that the early bone loss occurs more in the trabecular bone compartment, right? And one of my hypotheses is that if the bone loss has actually entered into cortical compartment, it is probably too late, right? And we really need to actually detect bone loss when it is still confined in the trabecular compartment. So we also actually did a meta-analysis to justify why we really need to look at bone microarchitectural metrics rather than just bone density. So what we did actually a meta-analysis of 38 studies that were actually reported during 1985 to year 2000s, and looked at actually the predictive parameter R value, right? The R value had actually where BMD is used to predict bone's mechanical behavior, right? And what we have actually seen that the R square is kind of distributed everywhere. Right? Some of the studies have shown actually very high correlation between, or very high predictive power of BMD for bone's mechanical behavior. But then there are also lots of studies in this area where actually the predictive power is very low, right? And on an average, the average predictive power was actually R square was 0.64. What it means that around 64% or 65% of variability of bone's mechanical behavior or bone strength can be explained by bone mineral density, and rest is coming actually from, and the remaining is coming actually from bone microarchitectural makeup and the quality of the bone microarchitecture. So actually people started looking at actually correlation between bone microarchitectural measures and actually fracture risk or bone strength. In early days, people use actually histologic studies. So what histologic studies means is basically you do a bone biopsy at iliac crest or at rib, all right, and then either you slice them in 2D and look at bone microarchitectural metric, or you actually do a very high resolution ex vivo imaging. It's called micro-CT imaging, where you can achieve a resolution of say of the order of like 10 micron or even lower, even higher resolution. And then you can actually from this micro-CT image you can also actually look at microarchitectural measures. But this actually study is not suitable for control, right? and also it is not actually applicable for time series or longitudinal studies, because once you actually remove the bone is lost, and it takes around 6 months to heal the bone, and even if it heals the bone, the microarchitectural makeup will not be the same. Right? So there are limitations. So what we started our research was actually developing what we call virtual bone biopsy, right, where we actually acquire in vivo imaging, right, to actually segment or separate the individual trabecular bone, and then take out a bone core from a anatomically consistent region and look at bone microstructural measures, right? So since these are in vivo imaging, the challenges are reduced resolution. So because despite the tremendous advancements in emerging imaging technologies, still at present the image resolution is actually lower or of the order of trabecular bone structure, and therefore actually the individual trabecular appear in a very fuzzy way. Okay, and also limited signal to noise ratio is another major challenge, and that actually sometimes creates artificial breaks along the trabecular microneuron network. And also actually so we have to live with this. Then actually there are actually also a series of histologic studies that have shown that that among all other trabecular microarchitectural measurements, trabecular plate rod microarchitectural distribution is a major is actually an important microarchitectural metric that can characterize bone strength and fracture risk. And a large number of histologic studies have shown that gradual conversion of trabecular plates to rod is associated with increased fracture risk. And these are the list of actually some of the studies. I'm not going through those. So there was actually a time where there was interest in characterizing in a quantitative way, characterizing trabecular bone plate rod microarchitectural distribution from in vivo trabecular bone images. In early days, people used actually 3D Euler Poincare, where basically this Euler Poincare formula, it relates the number of tunnels, number of objects, number of tunnels and cavities with the number of nodes, edges, and faces. So we can actually in this the terms on this side can be easily computed from a voxel image, a 3D digital image, right? And then for the terms on this side, we know that bone is a connected object, right? There cannot be a floating bone. So the number of object is 1, and there cannot be a cavity because body fluid has to enter everywhere. So the number of cavities is 0, and therefore you can actually, the terms on this side gives you actually the number of tunnels. Again, the number of tunnels is basically often expressed as the connectivity index. How well connected is that network? So this has been used in early days, but this we showed that this metric has a problem. The metric has a problem because if we actually break one trabeculae, right, we're losing one connectivity, right? But if we actually perforate a trabecular plate, we are actually we're adding 1 to that connectivity index because we're creating one tunnel. So the same physiological process of bone loss, when it actually breaks a trabecular rod, it reduces the connectivity index, and when it perforates a plate, it increases the connectivity index. So it has actually two opposite impact or effect on this index, and therefore the final results, it gets diluted and loses its accuracy and power. And that's why it has not been so. Later actually people actually identified those limitations and become less and less popular. Then actually there was another method that is still actually being used. It's a nice idea. The idea is, they call it actually structural model index. It's called SMI, what you are doing is basically you are computing the rate of change in surface area with dilation. Okay, basically, and it can be shown that if we have actually more rod-like network, then it will have actually larger SMI, right? But if you have plate-like structure, it will have less SMI. Okay? And this is actually a very nice idea, and is a very elegant matrix. But one major limitation of the two major limitation of this metric, one is that it's a global measurement. You cannot actually identify individual plates and rods. And then another limitation is that, because of this computation, you really need a very high resolution image, and therefore it is. People have shown, and studies have shown, that this is actually a powerful measure for ex vivo imaging or micro-CT imaging, where we have actually a resolution of the order of 10 micron. But like for in vivo imaging, where like voxel size is often greater or of the order of trabecular thickness, this is actually less accurate. So like we developed actually what we call is digital topological analysis. And this, I developed this during my PhD study, and at that time I didn't know the application. I developed it actually just because it was mathematically interesting idea. So if we have actually a structure which consists of 2D and 1D manifolds, right? And then by looking at local topological numbers, we're looking at 3 local topological number of actually objects, number of tunnels, and number of cavities, right? By looking at this number, I can say that like this one belongs to a 2D manifold, that means a plate-like structure. This belongs to actually 1D manifold. This belongs to actually junction of 1D manifolds. This belongs to a junction of like 2D manifold. This belongs to a junction of 1D and 2D manifold, and so on. Right? This is very well defined in continuous space, but in digital space it is not so well defined. But like we have actually we had to struggle a lot, but eventually the good neat thing is that we have been able to solve the problem in digital space. I'm not going into that much detail, and then it has been applied to in vivo trabecular bone image. This is actually an in vivo trabecular bone image. This is actually the skeletal version of an in vivo trabecular bone image, and actually our algorithm automatically identified trabecular rods which are colored in red, and trabecular plates which are colored in green, and there are actually few junctions which are colored in blue, right? And this actually has become a popular method. So here we actually applied in MR images, like in vivo MR images from 4 different subjects. One is actually healthy young adult, and then it is osteoporotic old volunteer. And from here to here, the plate to rod ratio or surface to curve ratio changed from 58 to 3.5. So almost like more than 15-fold change in this microarchitectural measures. But the bone volume fraction change only by 60%. All right. So 60% change in bone density or bone mineral content actually leads to 15-fold change in the microstructural measures. So you can actually see these microstructural measures is kind of more like a magnifying glass to assess osteoporotic bone loss. And this has become a standard method and is widely being used in many studies at many leading institutes in US and also in Europe. You see, yeah. So, like later, later we further advanced this technique from here to here. The difference between here and here is that here the classification of plates and rods are actually a discrete classification, either plate or rod, right? But what you will say somewhere here, all right, where you will draw the threshold. So what we developed here is basically a classification on the continuum between perfect plate and perfect rod, right? And this is actually a color coding on a volume image, volumetric trabecular bone microstructural image, and you can actually see it matches with what you visually see. And these colors were actually assigned and created by the computer. And here, for example, here is perfect rod, and it gradually becomes perfect plate. Okay. So it accurately, so basically because of this additional power of classifying them on the continuum between perfect plate and rod, it has more accuracy. It can accurately capture gradual conversion from trabecular plates to rods at the level of individual trabecular. Right? So in terms of actually in vivo imaging technique, in our lab we actually we are pursuing the multi-row detector CT imaging as a viable modality for in vivo, where we actually we scan the distal tibia, right, and you can get a high resolution image. You can see the individual trabecular microstructure. It's a very high. It gives you a high spatial resolution. It has actually a resolution, in-plane resolution of 167 micron and 287 micron, in the slice direction or in the z-plane resolution. It is a very like a high-speed scanning scanner. It can scan 10 centimeter in just 6.8 seconds, and therefore actually it can significantly reduce motion artifacts. Okay? And then it's ultra low radiation. The total radiation, the effective radiation is around 50 microsieverts, which is equivalent to I think 5 days of background radiation, close to 5 days of background radiation. And it has actually large scan length, and since it has a large scan length, we can actually retrospectively identify the VOI for bone microstructure measures. So it eliminates the positioning error. Right, which is actually a very significant challenge in other imaging modality, where you don't have actually that luxury of scanning that large scan length. For example, HRPQ-CT or MR imaging. Okay, so from this from the CT scan, high resolution CT scan, we can segment the cortical bone microstructure, cortical bone. And we can actually reconstruct the 3D trabecular bone micronetwork and then classify individual trabecular plates and rods, right? And basically we did actually a repeatability study, and what we have found, these are actually the metric that we actually recently pursuing in our lab. This is actually the SMI. This is the SMI. And this is actually the erosion index that we developed earlier based on our discrete classification. So you can see that these methods actually, our recent methods are actually very highly reproducible, right? And if it is reproducible even actually for a very small VOI size of with diameter, I think around 4.5 or 5 millimeter. Okay, that means you can actually do regional bone loss for the case of heterogeneous bone loss. Okay. We actually compared with the micro-CT, like CT and micro-CT based measures. You can see that micro-CT can actually, it is a very high resolution imaging, so you can actually detect more trabecular microstructures than regular CT. But if you look at like a regionally you can compare, in a regional sense, there is an agreement between micro-CT and MD-CT. And similarly, this is actually plate rod classification, and this is actually transverse and longitudinal bone classification. So red are actually transverse bone, and green are actually longitudinal bone. And again, you can see regional agreement. So we did actually a comparison between micro-CT, and it actually gives actually acceptable correlation, where the correlation is close to actually like greater than, for many measures is close or greater than 0.9, which is good correlation. All right, so these are actually the list of measures that we actually provide from in our lab, which is called volumetric BMD. It's called transverse BMD. That means the bone mineral density contributed by transverse trabecular structure. trabecular bone network area, trabecular bone plate width, trabecular plate to rod ratio, trabecular thickness, and trabecular spacing. And we also actually provide erosion index. This is actually our old metric, and the structural model index. This was actually developed by other group. And we can actually see that it has actually a high correlation between microcity and MDCT based measurements. But the values are actually still not the same. The values are different, but there's a high linear correlation, except the trabecular thickness. It has relatively lower trabecular thickness, and spacing has relatively lower correlation. And this can be understood because, as I said, the resolution of MDCT or the clinical CT scanner is actually voxel size is either larger or comparable to trabecular thickness, and therefore actually that error in thickness measurements is actually can be understood. Right. We did actually mechanical test experiments. What we did, we actually took out trabecular bone core from cadaveric ankle specimens and did actually mechanical testing to get Young's modulus from the linear section of the stress-strain relationship, and this is actually the correlation that we have found for different metrics with yield stress and Young's modulus, right? And you can actually see that the microstructural measures, they have actually high correlation than volumetric BMD. More interestingly, this is actually we looked at actually. If you look at this slide, this is a very interesting observation. So what we did is that, like, for each specimen, so each curve here represents one specimen, one trabecular bone specimen, and the curve represents the BMD of that BMD distribution of that specimen at different trabecular plate width. All right. So the area under the curve gives you actually the total plate width. Total BMD. All right. And basically, the area under the curve for this section, it primarily gives you actually BMD contributed by trabecular rods. On the other hand, area under the curve for this section is primarily contributed. Is the BMD primarily contributed by trabecular plates, right? And then we color coded them based on their experimental bone strength. So the green curves are coming from strong specimens, and red curves are coming from weak specimens, and your orange and yellow curves are in between, right? If you look at this section of this plot, there is really no uniform color grading. You see orange, red, green, red, something like this. Color is more haphazard. But if you look at this part, in a statistical sense, there is a nice grading from green to red. All right. So in other words, in determining or in predicting bone strength, the BMD contributed by trabecular plate is kind of behave more like a noise. And the primary and majority of the signal is coming from the BMD contributed by trabecular plates, right? And our method allow you to separate these two BMDs. And these observations can also be actually explained physiologically, because during the bone loss, like some of the plates, some of the rods are lost, and then some of the plates are actually converted to rods. So depending upon which process is going faster, you'll actually see like more rod density or less rod density. But here, during the bone loss, there is only one directional conversion, and that conversion is from plate to rod, right? And therefore, you have actually such a nice power of predicting bone strength from using the BMD, trabecular plate BMD. And this correlation plot tells you the same story. So here you have actually BMD, right, and yield stress, and you can see the R square. This is good R square. R square is 0.79. But when actually you just consider the plate BMD, that means the area under the curve for this section of those curves you see a very high correlation. R square is 0.992, almost like a straight line. Right? And this is actually a very powerful tool that our method can provide. Okay, so I'll actually, how I'm doing in terms of time. I think I'm fine, right? So let me actually briefly tell you some results from our human studies. So this is actually an MR-based human study. So what we did, we recruited like 10 subjects with like 10 hypogonadal subjects. So then hypogonadal men, actually. This is actually a study on men. So the hypogonadal men means actually they have less sex hormone, and then like 10 age, BMI, and race matched eugonadal. Eugonadal means they have elevated sex hormone. So 10 hypogonadal and 10 age, BMI, and race matched eugonadal subjects, and then we actually acquired their MRI, ankle MRI scans. And this is actually their plate rod this is actually BMD distribution at different trabecular bone plate width. And what we see here again, that this part there is really no statistical separation between. So okay, so the rates are actually coming from hypogonadal subject, and actually green are coming from eugonadal subject. Now, if you look at actually this section of the curves, there is no statistical separation between red and green curves. But if you look on this section of the curves or the plot, you see some statistical separation between red and green curves, right? And what we actually, when we did a quantitative analysis or statistical analysis, what we found is that there was actually 44% greater trabecular plates in eugonadal men as compared to hypergonadal subjects, right? And the p-value was very significant. P-value was 0.001. But there was no significant difference in rod volume, and that's what we see here. There is no statistical separation between red and green curves. Well, then what we did is that we actually followed the 10 hypogonadal subjects for 2 years. And we treated them with sex hormone, the testosterone hormone, and then we actually scanned them at baseline, right? Then after 6 months, after 12 months, and after 24 months, right? And this shows actually the plate rod classification from the ankle MR scans, right? And as you can see that there is actually nice conversion from reddish bone to more greenish bone, right? That means more plate-like structures, right? And our statistical analysis showed that after 6 months, there was 6.5 time increase in trabecular bone plate rod volume. It marginally failed to be statistically significant. This p-value 0.6 is sometimes called suggestive significance, all right? But like after 24 months, there was actually significant, very significant, like 16.2% increase in trabecular bone plate volume, right? And you can see that p-value is actually 0.003. But there was no significant change in rod volume even after 24 months of treatments, right? And the beauty of this, as I mentioned earlier, the beauty of our method is that it actually allows you to separate these two types of structures, right, from in vivo scans. You know what in vivo means? In vivo means actually in living person, like when we go and do a scan. Ex vivo means actually from a cadaveric specimen, we take out actually some piece and do the scans. Okay, so this is actually results from this results from a CT based study. So we recruited 30 patients, 16 were female with COPD. So COPD is called chronic obstructive pulmonary disease, and studies have shown that those patients, they actually have metabolic disorder, and they have actually reduced bone and muscle strengths, right? So we recruited those subjects with the gold COPD gold status, means actually their disease severity. So higher the number, more severe is the disease, right? So we recruited 30 patients with COPD gold status between 1 and 4, and generally these are older patients, right? And their average age was 70.5 years with standard deviation of 8.3. Their body mass index, which is abbreviated as BMI, was 27.8. Right, it's basically the it's kind of like the healthy, the normal BMI, and their smoking, smoking pack year, was actually 40.3. So for 40 years, that means their smoking is equivalent to 40 years of smoking with daily one pack of cigarette smoking. Okay. So like among this 30 patients, 21 patients had at least one vertebral fracture. Okay. 10 patients with one, and 11 patients with more than one vertebral fractures, right? And this is actually the bone microstructural network from at distal tibia, right? For a subject for a male without actually a vertebral fracture, and this from a vertebral fracture. And you can see here is a nice and compact trabecular bone micro network with more trabecular plates, as compared to here is more porous microarchitecture and more trabecular rods. And then actually BMD, but the difference in BMD was not that much, right? I think the difference is close to how much, maybe 6, 7, 8%, something like that. But there is actually very significant difference in trabecular plate width, right? So the patient without a vertebral fracture had 50% more trabecular plates, which is actually. But if you look at the volumetric bone density, difference is not that much. So we actually did a statistical group comparison, and what we have actually see that this is actually for no fracture group, and this is actually greater than one fracture group, all right? Greater than equal to one fracture. That means this is actually fracture group. So this is actually the mean and standard deviation of different measurements. And you can actually see these are actually the trabecular bone microstructural measures, and these are cortical bone measures. And this is very interesting to see that there is a significant difference in actually trabecular bone microstructural measure between fracture and non-fracture group, but the difference between cortical measures were not statistically significant, right? And the fracture group difference in trabecular bone microstructural measures, it remains significant after adjustment with age, gender, and COPD status. So basically, it suggests that this microstructural difference between this fracture and non-fracture group is more inherent and is not a byproduct of of age, gender, or COPD status difference between the two groups. Okay. Well, these our methods are actually being used in a large number of ongoing studies. So this is one study where I'm the PI. Basically, we are developing a CT-based, we are trying to develop a CT-based model of bone microstructural measures to predict fracture risk in COPD patients. These are three studies that are actually ongoing at New York University, where Greg Chang is actually the PI. So they are mostly using MRI, hip MRI, all right, and actually looking at different biological and clinically related questions, trying to answer those questions using our method. This is actually a study that is going at the University of Iowa. Dr. Stephen Levy, he is actually the PI of that study. And this is basically the objective of the study is to actually look at the impact of fluoride intake and other other actually lifestyle factor on bone development in childhood. And then actually this is actually a nationwide study where Professor Turner, he's a PI from the Iowa, and basically it's a multi-center knee osteoarthritis study where we are actually trying to actually see what is actually the interaction between between osteoarthritis and change in bone micromechanics using bone microstructural measures. So that's basically the core scientific question that we are trying to actually answer in these large studies. This is another study from Baylor University at Houston, and basically the objective of this study is to actually look at the impact of anti-depression drug on musculoskeletal health. So there's another study that recently got funded. Again, the PI is a collaborative study with the Baylor University, and in that study we're actually trying to look at actually bone development or bone loss in actually type 2 diabetes. So some of the recent development, let me actually very quickly go over this. So as I mentioned, in our lab we are actually pursuing like emerging CT technology as a viable in vivo imaging technology to get bone microstructural and cortical bone matrix. But one challenge in using clinical CT scanners is that there is actually wide range of CT scanners, and the resolution the resolution features and other image artifacts are different for different scanners from different vendors, or even actually from different scanner model from the same vendor. So it's important to actually, so when you're actually using this kind of imaging technology in a study, it is very important to harmonize the data coming from different scanners. And here we're actually using deep learning to harmonize this. So you can see this is actually data from a low resolution scanner, and this data from a high resolution scanner. And using our deep learning method, we can actually we can predict the high resolution image from the low resolution image. And you can actually see they're very similar. In fact, this one looks actually more like a smoother version of this image. So there is another recent developments, and these papers have been actually recently published in Medical Physics and Radiology, which are actually very prestigious journal. So what we are actually doing here is basically we are developing a computational bone mechanical analysis technique where we don't need to actually segment or separate the trabecular bone microstructure, rather actually like treat the bone mineral density on the continuum between 0 and full bone, right? And that basically you can actually see this is actually the BMD, and this is the stress flow, and you can see the stress is flowing primarily along the trabecular bone microstructure without requiring segmentation of trabecular bone micronetwork. And therefore actually some effect of noise is significantly reduced. At the same time, we can actually characterize the strength of trabecular micronetwork, right? This method has been actually validated using micro CT imaging, and also actually you see that there's a very high correlation, R value is 0.84. There's another thing that we are actually developing. Basically, here we developed a method where we can actually segment the proximal femur from clinical CT scanners, and I don't have the slides here, but we can also not only segment them, but we can actually identify different anatomic regions and do actually mechanical analysis and actually bone density analysis at different regions, and relates it with aging, with different factors, risk factors. and also their ability to predict fracture risk. Well, this is another direction that we are recently pursuing. So basically, we are actually trying to develop a method where you can actually segment the spinal column from chest CT scans, and not only you can segment them, we can actually label individual vertebrae from there, and we can automatically detect which of them have actually fracture and non-fracture. And this is actually a very powerful tool, and that would allow us to actually apply our method on a very large data set, and we can actually find very interesting and novel clinical and biological findings from those kind of study analysis. And recently we have submitted a grant along that direction. Basically, we did actually an ROC analysis of our fracture detection algorithm, and we have actually found that we can actually get 96.9% accuracy, right, with sensitivity and specificity of 95.5% and 97%, and this is actually very high performance, right? So this method is now ready to be used in large studies. Well, in conclusion, I'd say that trabecular bone plate rod microstructure is important to characterize osteoporosis and fracture risk. Multi-row detector CT is a potential imaging modality for in vivo assessment of bone microstructure. And multi-row detector CT-based bone measures may be useful to predict fracture risk. And musculoskeletal degeneration is a major comorbidity in lung disease, and is worthy to quantitatively understand various links among the related factors which are related to both COPD and factors not related to COPD. So these are the major direction of my research direction. I must acknowledge my collaborators, scientists, postdoctoral fellows, and graduate students. And finally, I need to actually acknowledge the grant supports. Without the grant support, we would not be able to do anything. We really need grant support. So that's all. I must thank you. And I'm ready for your questions.
Yeah, thank you, Dr. Shah, so very much, because the topic is so interesting that I just cannot tell you.
Thank you. Thanks.
And your presentation was very lucid. So first, let's give a very, very big hand to Professor Saha.
Thank you. Thanks.
And thank you so much. I think I cannot just see any question answer, but of course there is one question from our listener, our audience. So Professor Shubhadev Basu is asking that can we apply this plate rod extraction algorithm to other applications where shapes are more like spheres or ellipsoids connected to tubular structures?
That's a very good question. And so that's actually that's what we are doing using our tensor scale based analysis. So what we do is basically we model each locally model a structure using an ellipsoid, and then you can actually analyze the geometry of the ellipsoid, and then you can actually characterize the ellipse. Then the structure is whether it's more elongated structure or it is more plate-like structure. And I think that I know you are working on on your spine project, very high resolution 3D, and I think there is actually room of application for this. Yeah,
yes, because nice, I think earlier, yes, the question is very appropriate, it seems, because earlier you have mentioned that it's a generalized, area, you cannot just localize it. So with this, the answer that you now gave, I think it will be used for localized.
So basically, the previous method, the structural model index, that is actually more global measures, and you cannot localize it. That's what I think you are
Yes.
pointing.
Yes, yes, yes.
But yeah, so that's actually the beauty of our method, where we can actually localize at individual tubercular level, and you can say whether there is that particular tubercular is more plate-like or rod-like, and therefore, since you can do that, you can actually get those distributions of like DM distribution at different plate width. So it is not only giving a metric, but it gives you a distribution of tubercular plates and rods
Yes.
in a bone. So, yeah.
And maybe for that matter, those deep learning techniques will also be required to just get the image more clear, whether it is from high resolution or low resolution scanner.
Yes, yes. So there is a big room here of research. I am not pursuing it, but there is an opportunity here. Is can we actually use deep learning to achieve these kind of things without without actually going through our methods and all those things? Can you use deep learning to accomplish this task? Yeah, and maybe actually it may be possible that deep learning will give you a more generalized measures across images from different resolution, and that would be very interesting thing to pursue. But as we say, like here actually, like you always have to get funding before you can initiate a research, and it would be difficult for me to get funding along that direction than actually for studies which are more clinically and biologically more interesting. Yeah.
So you are getting this data from different clinical labs, or you have a scanner, and you have a high resolution scanner, I believe.
Yeah, we have actually all kind of scanners. We actually I have an appointment in radiology, so I'm part of the hospital.
Yes.
So we have actually access to the scanner. We have actually one dedicated scanner, for research.
Very nice. It's really very inspiring that you could go to such level, and you are thinking in the direction of that spinal cord one is very, very, I think, appropriate and effective that study would be.
Yeah.
Because it's really.
Yeah, that's actually that's the advantage here. Actually, like you can design a study, because in order to answer, first you have to find a novel clinical question, and then in order to answer the novel clinical question, you can actually design a study, and but you need a funding for that. That's a hard part, actually.
Right. I think Professor Basu has another query in the context of 3D images of neuronal spines that often have, blobby spine heads connected to dendrites having tubular trike structures.
Yeah, that's what I meant that actually. I didn't remember the exact name. It's a neuronal spine.
Neuronal spines.
Yeah, so yes, definitely you can do that. You can actually characterize, you can apply our analysis, and you can actually locally characterize, and you can actually maybe you can use that to actually separate the head from the stem, because stem would be more more tubular structure, and head would be more like a rod-like structure, right? So you may be able to actually use this to separate them. That's what I meant actually. Yeah. Thank you. Is there any other question?
I don't think there is any more questions. So
yeah,
thank you.
Thank you again.
Thank you for having
me. From Professor Bosu, that my query is in context of 3D image neurospinal spines that often have blobby spine head connected to dendrites having tubular type of structure. This is not directly a question. Some queries there from Professor Bosu. Can you see this one that I can see from YouTube actually?
Yeah, we can see that. I think we have discussed it, and I believe we have answered it. Yeah.
Okay, you answered that. Okay. If I don't see any more, I cannot see any more queries. So we can, I think, thank you, Professor Saha sir, Professor Neogy, madams, would be happy that had you have been physically here, so we could have at
Yeah.
least felicited you in our traditional way here in Shillong, Meghalaya. Hoping that in future, at least one of you will be here in some other conference in near
Yeah,
future.
hopefully it will happen sometime.
Thank you, ma'am. Thank you.
We
Thank
also
you,
hope
sir.
so.
Thank you.
Thanks.
Thank
Thanks,
you.
Sarmistha.
Thank you
Very
all.
nice to see you.
Yes,
Yeah.
also the same here.
Kolkata gele dekha hobe.
And sure. Of course.
Okay, bye.
Okay,
Okay, sir.
bye-bye.
Okay, bye.
Bye all.
Thank you. Thank you.